Hi friends, welcome to our project demonstration. We are students from Welltech Multitech Dr. Rangarajan, Dr. Shakuntala Engineering College. Our project consists of three members, myself Sham, my team members are Gokula Darshan, Vetrivelas. Our project title is Design of Microstrip Patch Monopole Antenna for Pancreatic Cancer Reduction. Our project is guided by Dr. K. Chandrakala, Associate Professor. Hi friends, as I briefly introduced our project to design and develop a microstrip patch monopole antenna that can detect subtle changes in electromagnetic properties of tissues that indicate the presence of cancer. It ensures energy is directed toward the target area, improving diagnostic accuracy. Manufactured using standard materials and process, it is affordable for wide-scale use. The direction of cancerous tissue allowing for timely treatment. This technique holds the potential for non-invasive real-time monitoring, which is crucial for early intervention and treatment planning. As the monopole antenna known for the simplicity being explored for the potential in medical diagnostics due to their ability to detect subtle changes in tissue properties, as they are relatively simple in design and make easier to fabricate and integrate into diagnostic devices compared to more complex antennas. Antennas are widely used in medical application for diagnostic and treatment that transmit and receive electromagnetic waves which interact with body tissues in unique ways. And now you can see the antenna design on your screen. The antenna is designed using software called CST Studio, and the antenna is divided into three components in the antenna, ground and substrate, and the dimension of the every component have been listed. The ground plane is placed in the axis by selecting the rectangle symbol and entering the values of length and width as per design construction. The shape of the patch is used here is circular. The microstrip patch monopole is mostly commonly used on different shapes because it produces linear polarization and are also easy to fabricate. Also, it reduces low cross polarization. The microstrip patch is fed by microstrip feed, whose inner conductor is extended up to the patch through the substrate and is soldered to the metallic patch. On the other hand, and now to create a realistic human pancreatic phantom in the same software CST Studio, a structured approach is followed to design, simulate, and analyze electromagnetic response of both healthy and tumor affected pancreatic tissues. The primary goal is to construct a 3D model that accurately represents the pancreas along with surrounding organs such as liver, kidneys, spleen, muscles, fat, and skin. Each tissue component is assigned specific electromagnetic properties including relative permittivity, conductivity, density based on established biological data. The pancreas is modeled as a central organ with the tumor embedded inside it, positioned according to the clinical observation. Tumor properties differ from normal pancreatic tissue due to increased cellularity and water content, resulting in higher permittivity, conductivity, and density. The simulation process brick-shaped structures are used to represent different tissues, ensuring an anatomical accurate model. A fine mesh is applied in CST Studio to enhance precision, particularly. And now you can see the simulated designs of a design microstrip patch monopole antenna. The return loss of the microstrip patch monopole antenna is minus 26.29 dB. Antenna with a bandwidth of 1.1 GHz to 6 GHz. Return loss less than minus 10 dB implies that power is reflected back from antenna due to an impedance mismatch. Return loss which has more negative values is considered good, thus an appropriate level of power is able to be transferred to the antenna. Then the given graph displays the voltage standing wave ratio of microstrip patch antenna between 1 GHz to 6 GHz range. As a rule of thumb, VSWR is regarded as one of important metrics in antenna system as it analyzes the impedance matching ratio between the antenna and transmission line. This fluctuation indicates resonant frequencies where the power acceptance is greater, probably because of interaction with simulated system or phantom model. The peaks are at 1.5 GHz, 3 GHz and 4.5 GHz, showing frequencies at which maximum power is being absorbed. On the other hand, some dips in the curve represent frequencies at which power acceptance is not as much. Less energy is being absorbed or transmitted effectively. The accepted power values in the graph is about 0.01835 watt. And the gain and directivity plot of the far field electromagnetic and electric and magnetic. The values of the parameters involved for the proposed antenna and the dimensions of the parameters have been given in the field of microstrip patch monopole antenna. The values of the parameters involved and now the values of human tissue that is used in the pancreatic phantom designed in CST studio, the specific shapes and their positions are such that they approximate the anatomy of abdomen of a human body. Each tissue component is assigned accurate material properties to density based on established biological data. Take for example, the pancreatic tumors were given a greater density, which is 1100 to 1050 kilogram per metric cube, a higher relative permeability of 55 and a greater conductivity of 1.8 that normal pancreatic tissue due to the greater cellularity and water content. And now the fabrication of the antenna is done. When fabricating the microstrip patch monopole antenna, the right material must be chosen in such a way that it will result in highly efficient operation at the desired frequency. It is important to discuss the role of substrate material in defining the electro properties of the antenna. The designer's choice of FR4 exposures having a relative permittivity of 4.4 is due to its being the most cost effective, and it is easy to make it, and therefore has a good mechanical stability. The copper is generally deposited on the FR4 substrate through a chemical electroplating process to ensure the uniformity of the conducting tiers. The feed line and patch, which are parallel, were designed by etching the copper layer using photolithography methods or CNC milling to attain exact dimensions. The tumor results is shown on the screen. To determine whether a tumor is present or not, a comparative analysis of a return loss, voltage standing wave ratio VSWR and specific absorption ratio, that is SAR, is performed. In a normal pancreatic tissue without a tumor, the return loss shows a dip at a specific frequency indicating efficient impedance matching and minimal signal reflection. The VSWR value is also low, meaning that most of the transmitted power is absorbed effectively, ensuring stable antenna performance. Additionally, the SAR value remains within a safe limit, showing uniform energy absorption in the tissue. The return loss constitutes one of the most critical parameters in the evolution of performance of a micropatch antenna targeted towards pancreatic cancer direction. The picture shows the return loss of the pattern of the antenna in absence of tumor in pancreatic tissue. The return loss at frequency 5.495 GHz is at minus 15 dB, which provides evidence of efficient impedance matching and poor signal reflection. Return loss values lower than minus 10 dB indicate that much of power transmitted is being absorbed and not reflected. This proves that antenna is well suited for biomedical purposes, especially for identifying normal pancreatic tissues, which is highly important to detect for any abnormalities or tumors. And the VSWR without tumor is also shown in the figure. The best impedance matching is recorded at frequency of 5.94 GHz, where the VSWR recorded as 1.43. Reflection of the signal is low and indeed efficient. The power transfer into the tissue is performed effectively. This collaborates out finding that when a tumor is not present, the smooth performance of the antenna is observed, which includes stable impedance matching. This observation shows the efficiency of the antenna when dealing with normal pancreatic tissue, which is important as a comparison when looking for differentiating cancerous or abnormal growths. And now, the SAR analysis, that is specific absorption rate, is essential in establishing the safety and efficiency of microstrip patch antenna for detection of pancreatic cancer. The image presents that SAR is distributed at frequency of 5.495 GHz, where the highest SAR value was noted at 0.271681 in a 10 gram tissue sample. This value measures biological tissues, electromagnetic energy exposure and determines safe radiation exposure. On the contrary, the lowest SAR value recorded was 0, indicating the lower. The SAR results indicate that efficient biological tissue interaction is achieved, while the antenna is within the range of safe radiation levels of power devices, which substantiates the medical use of patch antenna for the non-invasive detection of pancreatic cancer. And now, the above images represent the return loss with tumor and VSWR with tumor. The effectiveness of microstrip patch antenna utilized for pancreatic cancer detection was assessed using return loss. The measurement and image shown depict the return loss on the above mentioned antenna, while a tumor in the pancreatic tissue is present at 5.49 GHz. The power transmission was noted to be 15 dB. The highest amount of signal reflection suggests accurate power transmission. And the return loss of minus 10 dB indicates that the tissue with the tumor is likely to be able to absorb and radiate appropriately. The return loss of the tumor tissue implies that the microstrip patch antenna may be able to detect minute variation within the tissue. And the voltage standing wave ratio, that is VSWR analysis for pancreas with the tumor, provided picture illustrate the frequency dependency of impedance matching for a pancreas with the tumor. It illustrates the range of frequency from 1 GHz to 6 GHz. Peaks at 2.2 and 5 show higher reflection signals. The gap that exists between 5.6 GHz primary frequency measured VSWR of 1.55 indicates a moderate impedance mismatch. Biomedical accurate microwave devices may suffer signal loss and inefficiency because of signal transmission distortion. VSWR of 1 indicates signal loss and detonation in efficiency for medical microwave. Now, the above images represent the return loss with tumor and VSWR with tumor. The effectiveness of microstrip patch antenna utilized for pancreatic cancer detection was assessed using return loss. The measurement and image shown depict the return loss on the above mentioned antenna, while a tumor in the pancreatic tissue is present at 5.49 GHz. The power transmission was noted to be 15 dB. The highest amount of signal reflection suggests accurate power transmission. On the return loss, the specific absorption rate, that is SAR analysis for the figure, is also presented on the screen, and the frequency of 5.6 GHz. The localized regions of interest in energy deposition are shown in more detail in the color scale deposition and for the tumor region. The highest SAR value is present due to high conductivity and high permittivity of the tumor. The tumor tissue SARs are essential for the safety and effectiveness control of microwave medicine, irregularity, advices, enforcement, and energy dosage optimization for tumor detection and treatment schemes. This result shows possibility of microwave imaging for pancreatic tumors detection under the different electromagnetic action onto the ordinary and cancerous bone tissue. However, to determine whether a tumor is present or not, a comparative analysis of return loss, voltage wave standing ratio, and SAR is performed. In the presence of tumor, the electricity properties of the tissue such as permittivity, conductivity change. This leads to noticeable shift in the resonance frequency and increase in signal reflection and a reduction in return loss magnitude. The VSWR value also rises, indicating poorer impedance matching due to altered tissue composition. Moreover, the SAR value in tumor affected region increases significantly, highlighting higher energy absorption because cancer tissues have different dielectric properties compared to normal tissues. This variation in return loss, VSWR, and SAR confirm the presence of tumor, making microwave imaging an effective tool for early pancreatic cancer detection and usage of antenna for a pancreatic cancer detection. The effectiveness of microstrip patch antenna in identifying pancreatic cancer VSWR analysis is important. The image given deposits the scenario when the pancreatic tissue is free of any tumor and shows the responsive VSWR graphically.